Yesterday we were looking for PN junction and we derived an expression which shows V0, which is the built-in voltage, is kT by Q ln Ne Nd by Ni square, or the other form we can write kT by Q ln T's of T upon N, or N's of N upon N's of T. This is what we derived, and we also said if there is a PN junction, let us say this axis we call x is equal to 0 because of the charge, diffusing charge, this is say P and N. There is ionized acceptors and donors on P and N side, and the assumption here is the charge density is always given by and we said that the charge density depletion layer is called in depletion layer we assume, it is not very bad assumption, there are no free electrons and holes. There are no free electrons and holes. Therefore, rho is Nd minus Ne, plus of course is assumed that everyone is ionized. And then we say on the P side, on the P side, I will have charge minus Q Na. On the N side, I will have charge density plus Q Nt. This is what yesterday we did. So we start ahead, and now maybe one more way we can derive this, that the built-in voltage occurs because of what? When P and N regions are brought together, holes from P see much smaller holes in N side, so they diffuse. Large electrons on N side see very small electrons in P, so they diffuse. But when they leave the junction, they leave acceptors and donors, which is called depletion layer. And in depletion layer, there is a charge density, and by Poisson's equation, dx by dx is essentially rho by epsilon. Where rho is charge density, and epsilon, we should write epsilon S, which is called dielectric or permittivity of silicon in our case, which can be written as dielectric constant into free space permittivity. So epsilon S is Ks epsilon 0, where epsilon 0 is free space permittivity, which is 8.85 10 for minus 14 rad per centimeter. We'll write down. Please remember, in my course, I do not use MK system, so you also should not. There is a lot of confusion goes in units, so numbers may change drastically in your units and my units. I always use per centimeter cube, per centimeter square, centimeters, everything in centimeters. So please do not get confused. There is no math requirement fortunately for us, but even that will be only in grams whenever half MV square term appears. So I always use CTS because over the years, pedagogically, for ages, all device people have been working in DGS system. Worst was, which you will not believe, but we used to say very funny, if you have a plan, I used to call 10 mil by 10 mil area. What is mil? Million or what? Milli of inches. Okay, 1,000 of an inch, which is 25 microns. Micron is 10 to the power minus 4 centimeters or minus 6 meters, but we say as I say minus 4 centimeters. So we used to declare area earlier in mil square, But the depth will say microns, 1 micron, 2 microns. So this is what device people have been doing, partly because Shockley did that way. And we all followed the way. So this is what I say. So please follow units because I figure out at the end some numbers change drastically. Also remember, do not leave Q anywhere because Q is 10 to the power minus 19 number which can kill the total value left and right. Like energy is Q times V and you don't write Q there, 10 to the power minus 19 times that will increase. So volt may appear like 10 to the power 19 volts and you may write also or square also finally. Never thinking that this kind of volt cannot exist. ऐसे सर को आता नहीं होगा number. So don't do this because this you have to understand. If I can create out my electron 10 to the power 19 volts, something great must be happening. पूरा energy problem solve हो जाएगा. So never try. So always look for correct units, correct numbers. So same way epsilon Ks, this Ks value for silicon, which I only will say Ks, is 11.8. Some books may use 11.9, some may use 12. Whatever number I will give you, that's fine. Is that clear? Some measurement show it is 12, some measurement show it is 11.9. I believe that most books believe 11.8 is good value and that's what we use. Epsilon at 0 is 8.854, third decimal चाहिए तो 10 to the power minus 14 farad per centimeter. Is that okay? So these values will be provided. There will be always the constant values will be given at the end of the paper. So use what value I give and what value you see. For example, I may give you KT by Q as 25.8 millivolts at 300 degree Kelvin, or I may say 25. So don't say no, I use 0.5. But जब दिया है वो use. Is that okay? So this is something which, so we can see from here, if d by dx is rho by epsilon, for n kind rho will be q and d, p kind will be minus q and a, and if I can then find x, okay, for n side and side, then I can also integrate x and get, is that clear? So one technique earlier yesterday we said, with another way is to look for the electric field profiles and then integrate the electric profile from the end of one depletion region to the other end and say this is the voltage contained in here. Okay, so we can always find built-in voltage by finding the electric field profiles. For different kinds of junctions, the field profiles. Now we'll say what are those junctions before we quit this area. Okay, so let me first do one of them, which I thought there are a number of ways. One can also write the Boltzmann relation, P is equal to Ni e to the power minus is about Ei minus EFP by KT. So I can write Ei minus EFP for P type poles, Ei minus EFP, maybe put 1 upon Q here, okay. Then I get, how much it will be? Sorry, KT by Q, ln, Na by Ni, where P is Na, P is Na by Ni. So in the P type, I can also write this relation because I know the Fermi level position, I have drawn the band diagram. So I know roughly it is something like this. By a similar argument, but this Ei minus EFP by Q is essentially the voltage drop on the P side. Energy divided by Q is the voltage drop along the P side. So this we call Vp. Similarly, I can calculate Vn, which will be KT by Q by ln Nd by Ni, and V0 therefore is Vn minus Vp, which is KT by Q ln product of the two Na Nd by Ni. This is another way of looking at this, because quasi Fermi levels tells you it's not really even quasi, there is no current, But even we say the carriers on the p side can be represented by Boltzmann relation. There is no current anyway. Thermal equilibrium is valid. So even if we use this kind of relations, we can always evaluate. The expression will come same as. So what does it tell? Essentially, why I am writing all these equations? On what factor the built-in voltage depends? Three things. NA value, ND value, and third, temperature. Is that correct? Temperature. So larger the temperature, built-in voltage will be larger. If the built-in voltage is larger, yesterday I showed you that the barrier will increase. Is that clear? So something at higher temperatures, there will be higher barriers. Is that correct? But we'll see that has some other bad effect on off currents. But otherwise forward it may be even better rectification. It may happen. So V0 essentially is constant proportional to only the doping on N side or doping on P side and temperature. And since we assume temperature is always constant in all evaluations, 300 degree Kelvin, room temperature 27 degrees centigrade. This is odd because in India this is correct, 27 degrees centigrade, room temperature. It is not odd number. In many other European and Japan and US, whether the room temperature may be less than 10 degree or 5 degrees, but they still use 27 degree as well. Because inside the room probably everyone sees 27 degrees. Is that okay? So that's the value why it's called room temperatures. Okay, so now let's go back and do something more, which is maybe we can calculate some numbers. Just to give an idea what is the kind of values you will get for V0. How much is V0 expected? Without thinking too much. How much is V0 expected? Leave at room. What is the typical value of V0 you expect? I already told you have seen cutting voltage somewhere in your measurement. Before that no current, obviously that must be around that value, but it can go up to what maximum value? Eg. So the maximum built-in voltage will be Eg. At that time all density of states will be P type, all density of N is N type, and in those cases actually you will have V0 is almost as you never achieve this value, so V0 will be always less than the band gap. Is that correct? V0 will be always less than the band gap voltage, which is 1.1 or 1.13. So larger the NA and D, larger is V0. If you really push it to denser states, then you may reach 1.1. So otherwise it will be always less than 1.2. So one example which I chose from the book. 10 to power 18 per cc. Please write units correctly every time the way I write. Do you know why I take such odd values here? 2.2 Ni square का term है, calculate करने में आसान. So V0, assume it 25 millivolt is kT by Q, Ln 10 to power 18 into 10 to power 16 2.25 into Ni square is again 2.25 10 to power 20. So if you do this, actually what I did is, but you can see from here, yes. I think we'll look at the sign, the minus Vp will actually, whatever is higher, from there you have to Vp, okay, so Ei minus EFP will still, if you put the opposite, you will get positive and negative corresponding. See, voltage is measured down, this is what I clear. Voltage is measured down, energy is measured upward. So you just measure accordingly, it will come sign. Just do it here. इसको मैंने कैलकुलेट किया है, ये 0.86 वोल्ट आता है. This is very high. Why it is high? If it is 10 to power 18 and this is 10 to power 16, you are coming closer to NC and V. Is that correct? You reduce this to 15, ln will be 1 less 10 of that. This will reduce to 0.68 or 0.72 or kind of. So the logarithm term. So what we are trying to say that depends on the NA and the values, you may get V0 which will be higher or lower. Maximum will go up to how much? 1.1 volt if all density of states are filled. That situation never exists. Okay. You cannot dope any material to that extent. Because what is the reason? Solid solubility of particular dopants is so much which is less than NCD. So it cannot reach that level, though we may wish it can. Okay. This is the problem. Now, or there is a possibility all may not get ionized even if you dope. That means they all do not replace silicon. There is no vacancy where they can sit. Which means what will happen? They will be in the existing site and actually create defects. So again, you never get full quota of electron holes at the conduction and valence. Okay, so this V0 value which I am showing you is to show you that the built-in voltage is typically of order of 0.6 to 0.9 volts, never beyond that. This is the range in which each value will operate. Now if this is the value, if I plot this expression across the junction, this is your depletion layer, this is your XPO, this is your XNO. What is O means? Thermal equilibrium, no power supply is still connected. So I see there is a potential, this is my Vn, this is my Vp, and this is my Vc. So from P to N, there is a potential barrier of V0 and therefore it will oppose any transport across P to N or N to P because there is a flip as if it is being itself. Okay, now this point has to be reassessed again. We have just said P's of P, some expression I derived, P's of P is equal to P's of N exponential 2V0 by KT. This is the expression of V0 rewritten. V0 is KT by Q, ln PT by Pn. So I write PT by Pn in this form. So what does it trying to tell us? If I plot a profile for this P's of P, which is very large value, P's of N, which is very small value, P's of P if you wish, and then exponentially it goes down e to the power PNO on the n side. From holes, large number of holes, they go down to a small number of holes on the n side. So there is a profile going on. Now if this is the profile which you see every now and then, okay, whenever this occurs, I can do little quick this also. P's of n can be written as, give me this value, P's of P in V terms, exponential, yes, minus EFP minus EI by, EVP by KT divided by NV exponential minus EFN minus EVN by P. Coleman relation is another form, is the density of state. But in equilibrium, what is equal between the two? What is the part same as in both cases? In thermal equilibrium, EFP is EFN. Fermi levels are aligned in thermal equilibrium. Is that okay? If that is occurring and I cancel NV, I bring it above, something I am going to get is P's of P, this is also equal to, e to the power 2V0 by KT is equal to whatever you divide this EVP minus EVN. n by t. Exponential. So if I equate this, what is the value of V0 I am getting? What is the V0 value from these two? V0 is equal to 1 upon, there must be some Q V0, so Q will also, here V0 is 1 upon Q EVP minus N. The band diagram which I showed you, band bending, do you see band bending? From EVP, it went down to EVN. That was the potential barrier, which is also provable that the change in bands from P to N same as UV0. Is that correct? So whichever way you look at it, because anyway we are only manipulating the same expression one way or the other. Okay, we are not doing this. We are just trying to show every way you go through it, you will find V0 represents, UV0 represents a barrier which is essentially band bending. Similarly, I can through ECN also, ECN, ECP minus ECN will also show me same V0 value, QV0. Same way if you see EI is in between, so bending EIP to EIN also will show me QV0 value. Is that correct? In thermal equilibrium, this built-in voltage can always be shown as band bending. Is that correct? Now having shown this, that finally, so now one can think of this. If I perturb this V0 by external bias, so what is going to happen? If I apply some bias, so this V0 term will modify. Is that correct? Because now additional voltage either may subtract or add, we will see how it does. And we will see that if I do that, then this relationship will not hold, because this was only true for equilibrium. Why it will not hold? Because then these two values will not be equal. Is that correct? And once you say EFPA, that means if they are not equal, or if I apply bias, current will flow. Is that clear? Because we say EFN and EFP are not same. There is DEF by DF going on, which means current will transport. So when I look for transport, the first thing I will show, where is my Fermi level motion? Which way it is going? If I sneak that line, I know current is flowing. Is that correct? This is the technique. So device to circuit, how do I look? What happens in device and what will happen externally, I can correlate now. How do I go up? So if I externally apply bias, which we have done in explain hopefully in the lab, then you find why currents flow when you apply bias, otherwise it does not flow. That essentially Fermi level shifts whenever current. Is that clear? Now this fact is therefore to prove my point that Fermi level movement is the cause of current is very crucial. But before we go to the transport, I want to derive few more things for you, and I want to know the profile for this junction. This I will rub off because I can use the same figure. This is x is equal to 0. Yeah, okay, doesn't matter. And now I want to plot Ex versus x. Electric field versus, I just told you earlier, the next point I want to find the field profile for the junction. And even now, no bias is zero bias. Actually, it's not even zero bias, it's open circuit. Zero bias is what case? When I short P and N, it's a zero bias case. This case is not a zero bias case. In zero bias, current may flow. Is that correct? Because as soon as you short circuit, something will happen like a battery discharges. The junction may actually discharge. But it doesn't happen for some reason, some other day. I'll explain you why it didn't happen there. If the diode गलती से ऐसा कर दिया तो कुछ नहीं होता. क्यों नहीं होता? ठीक है, वो अलग बात. उसका गेम है वो. Okay. If I want to find Ex, which equation I should use? Which equation is this? This is called Poisson's equation. Before I derive this, I may also like to tell you a few more things. If you have a PN junction and one side of the PN junction is heavier dope compared to the other, this is called P plus N junction, or alternatively it could be N plus P junction. One more possibility is what? P plus N plus junction. PN junction we already see, but it could be also P plus N, N plus P, or P plus N plus. The last one we'll see separately, so it's called tunnel diode. Yes, we'll see a different version. If I do so, now I figure out since P plus is higher than N plus, N, what does that mean? That the number of acceptors are higher per CC compared to donors per CC in the N side. So that's clear. One interesting feature which I want to prove later, which I'll say, if there is a depletion layer, let's say I plot depletion layer, the charges, first I'll plot ND minus NA. Let's say I plot this. I find that x is equal to 0, left of x is equal to 0, there is a large number of acceptors within a small x. Why it happens like this? Because area being same for the device, for the larger n you will require smaller thickness. Per CC में area common है. If n is larger, so x will be required will be smaller. Is that clear? So it's a sheet charge. Some kind of very thin layer of depletion will occur in the P side. Is that clear? I repeat, net charges will be same. Okay. Since the P has much larger holes or larger image, if the area of cross section is same, then thickness required will be a smaller. Area into small thickness will be larger per CC anyway you get. So for larger n, you will require smaller depletion layers on the P side. Vice versa, if it is n plus P, the depletion layer on n side will be smaller. Whereas ND being smaller compared to, this is your NA value, ND being smaller than NA, it will require larger depletion layer to create equivalent charges on the N side. Is that correct? So you see the depletion layer on N side, this is XNO, may be much larger sometimes than XP0, and the net depletion layer we call it W, which is W is equal to XNO plus XPO, and then we say it is equal to, if XPO is 4 orders smaller than XNO, that is 4 decimal term will change in XNO. Let's say XNO is 0.6 microns, XPO will be 0.0003001 microns. You are writing 0.60001. That accuracy is not relevant because it is a 4 decimal one. You say practically W is just as it. So one thing which we are now seeing, that if I want to have a diode, which is very good in this, that's what he said he wanted to learn capacitance first for his tomorrow's lab, so I thought I should do that. So I figured out that okay, where is the depletion going to? Depends on the diode I use. If it is P plus N, all depletion there will be mostly will be in N kind. If it is N plus P, most of the depletion will go in P kind. So XP0 is very small compared to XN0, never neglected. Why? Numerically you may neglect. Because if you make xp0 0, there are no charges on the p side, so balance will be lost. So xp0 absence is not possible. It has to be there, but that value will be much smaller as far as xno is concerned. So the total W equivalently saying it is xn0, but doesn't mean xp0 was 0, because then the acceptors as if not present, so there is no junction there. Is that clear? So one fact should understand that in many times we say everything is swept on the inside, swept on the inside, there is depletion occurs on the inside. I never say there is no depletion on the P side, but I say numerically that value is so small, I am not worried about number. But if it is not present, the whole junction theory will collapse. Okay. So in calculations I may neglect xp0 in many cases, but in reality I should always know that xp0 exists, otherwise charge balance is not possible. Is that clear? This fact has to be understood, because many books always write xno is W. You find how they replace. They replace because they see that numerically xp0 was smaller than xno, much smaller than the for number. This junction, in which on the x left side of this there was uniform concentration of Na, and suddenly at x is equal to 0 on its right, there is a uniform concentration of Ns, is called abrupt junction, abrupt, P to N. So this is one junction which, what is the other name it could be? You can see something like this. What is this? Can be step junction. So another name for this is a step junction. So in the step junction, because I want to solve that equation, therefore I thought first I show you. In a step junction, on your left of x, there is a step of P, A or Na, and on the right there is only Nd, both are constant. However, in reality, such a junction is very difficult to make, though we try a lot of it, because it's a most ideal junction to work. However, there are other possibilities exist. If I plot Nd minus Na, which is minus xno, which is xno. What does this means? Is graded linearly. It goes from P to N linearly. Okay. So Nd minus Na is proportional to the gradient itself. We call grade constant as D, that is slope of this curve. These junctions are called linearly graded junctions. The third possibility may be, or many of them in fact, you may have a diode which is essentially called, I don't know whether you heard this diode any time, but hopefully yes. This is called PIN diode. PIN. P-I-N. I think this course I may not show you, but what happens if this I is intrinsic, see, this is called hyper abrupt junction. It's called hyper abrupt junction. I can be smaller and I can mix both N and P grading, okay, and then I can create another junction which is called hyper abrupt junction. So there are varieties of exponential profiles I can create, error functions I can create, Gaussian I can create. There are a number of ways profiles can be. Ideally, what do I want? Step junction. Ideal on the left side, on the right hand. So all our solutions in theory we'll do because they are doing analytical. So we'll prefer abrupt junction analysis. But in real life, you want to have a simulation of device performs, you should actually use a real profile. Is that clear? Then you will require some kind of nonlinear systems will appear, equations will appear, and then you cannot easily solve them because either you should be so good in maths, which some of you may be, that you know when to linearize how much. So if you know how to linearize equations, you can still solve easily. Otherwise, go for Gupta or any third, second order, fourth order Gupta or any other technique. Otherwise, simple is Newton-Raphson. It solves everything easily. So you can always say that maths do help us to get more accuracy on it. Otherwise, what we will assume is things are ideal. That's what teachers do. That's what I teach. Just simple बताते हैं. और आपसे पूछो वो करो. इतना भी नहीं आता. That is teacher in me. So anyway, but when I was student, I did all of it. You don't worry. Okay. My teachers also must have done the same, है ना? तो एक जमाने में मैंने भी किया. Okay. So this, I may do this junction. I may not do hybrid abstract because this is slightly different. I may do this calculation for this, and of course I will do calculations for this because this is most dominant for me. So this I will like to do. So let's do this. If I have a step junction shown here, then I will write d by dx is q in d for x less than x no. For which case I am solving abrupt junction. So for the n side there is no p, we have already said in step, on the left only p, on the right there is only n. So I say for x greater than 0 less than x no, the only charges available to me are 2 in. Same equation I can write for the left side, minus 2 in E when x is less than or greater than minus no less than 0. I say the charges are only acceptors, so minus 2. So very kind of thing. Okay, maybe I can write FTF 0. Thank you. Rho is QNA and rho is QNA. Now if I have these two equations to different regions, where is the common boundary between the two? X equal to 0 is the common, so I must get values same from both sides or use same value and then say okay how it will go, either way. What mathematicians do, as I keep telling, in any lemma or anything they start with an assumption and finally prove the same thing QED. ऐसा सभी लोग करते हैं. तो ऑब्वियसली आपने एज्यूम किया तो वो आने ही ना फिर, कौन पूछेगा बड़े साहब से ना. Mathematicians think that if they are said it, this is the final word. Generally कोई ऑब्जेक्ट नहीं करता. Okay, please, if this is the equation, we'll solve this later. First we'll solve this. Dx is q in d y ks epsilon 0 x plus 1. Simple linear equation है. इंटीग्रल किया एक बार. अब हम कह रहे हैं, please, where your attention now. I say, please take this boundary condition properly. One, of course, I said at x is equal to 0, it is E0. But another thing I am looking at x is equal to xno, beyond that there is no, maybe I should do something like this. At xno beyond, I don't see any charges out. So on the inside, what are the charges there? Charge neutral. All semiconductors are charge neutral till you apply something to make it non-equilibrium. Otherwise they are charge neutral. When there is a charge neutrality, what is the field there? There is no field because there is no charges there. So we now assume that charge neutrality exists on this side and this side. So we say at x is equal to xno E x. There is no current, so the Fermi levels are aligned anyway outside. There are no free carriers because they will be combined and set fixed value to them, so no transport is possible. Since there is no space charge, there is no electric field. If there is no electric field, voltage across them is 0. There is no voltage drops anywhere. Is that clear? So we define this as our equation. Then what is value of C1? E1 is how much? Minus QND by Ks epsilon. See, at above, right of XNO, there are no space charges. So ND, NAs are 0. P and N type in thermal equilibrium. Yeah, ND because they will have to balance. There are no free charge, space charge there. Okay, only holes and electrons could be there. But they must be equal because there is no current going through this. So obviously what we are now saying that there are no current transport, no P or no N. They are balancing. N current must be balanced by the P current. So net current is 0. So drift current is always 0 on the right. So electric field is 0 on the right, electric field is 0 on the left. So at the edge, the electric field must vanish. Because if electric field exists, current will flow. There is no current flow going on and therefore we say at that point you must go to 0. If I write this, then this expression can be written as Q in D by Ks epsilon 0 x minus x. Is that okay? So I can derive an expression of Ex, that's what I promised you, that I will derive the field profile. So Ex is 2 in the Ks epsilon 0 x, you know, x minus x, you know. If you see Ex, at x is equal to 0, there is some value E0. So if I write E0, which is nothing but E at 0, okay, some write EM. Why they call EM? Maximum. Let's see why it is minus. So how much is the value of EM or E0 from here? QND Ks epsilon 0 XNO at x is equal to 0, the electric field is QND by Ks epsilon into XNO. Is that okay? Now this value is negative. This value is negative. So on this figure, where should I draw this? Therefore you have seen that I had put it down. Is that correct? So at this value is somewhere is my EM or E0 or E0 as in the book. At this point beyond, the electric field is 0. But if you see this expression d by dx, QND by Ks epsilon naught, what is the slope it is showing you? It's a constant slope going upward, positive. This value is 0, this value is E0. So what is the field profile? Sorry, touch it here. The field should rise from minus E0 towards 0 with the slope of QND by Ks epsilon 0. It should go up. If I do the same analysis for the P Cont, क्या दिखेगा आपको इधर? Let's do that first. Is that okay? This expression is clear. E0 is minus QND Ks0 into XNO. So this is the value which I got. From the Poisson's equation I am seeing d by dx is positive going towards 0 from E0 minus E0. यहाँ से यहाँ तक आया. So ये उसका profile. Is that? Can you think now that the other junction which I showed, like linearly graded or abrupt or something, this profile will not be linear then. Is that clear? Because this expression will have some x term appearing here. Is that correct? तो जब इसका x है ना, तो कुछ parabola बना सकता है, hyperbola भी बना, कुछ और भी बना. Right now it's a linear and that's what I say. Abrupt junction is simple, easy to understand. So we'll solve that. और आपको क्या पूछेंगे? Linearly graded, ये सब आपको. So write the second equation again for the other kind. Minus QNE by Ks epsilon 0 XPO D. On the left This is the Poisson's equation. Again I solve this with minus q in a ks epsilon x plus 1 at x is equal to xpo minus xpo, px is 0 on the p side. Same other boundary. तो क्या मिलना चाहिए आपको यस का टर्म में, कैसा दिखना चाहिए? q in a ks by epsilon 0 x plus x माइनस है ना, x माइनस माइनस ऑफ x, तो x plus. So how much is E0 from here? E0 from here I get q in a xpo divided by ks epsilon 0 minus because of both are minus. If E0 is q in a xp0 by ks epsilon 0 coming from the p side and coming from the n side, how much was this? q nd xno by ks epsilon 0 for n side. I derived from n side, I went to E0, I came from p side, derived it to E0. But what is the theory says? At one, okay, similarly for this one, I should get this kind of slope minus xpo to 0, it will go down. Is that okay, ma'am? This is minus slope ऐसा है. So you get a triangle. Now can you tell me, if both sides I reach the same position, that means these two values must be equal. So I say q nd xno is q nd xpo, q also cancels. So nd xno is equal to na xpo. Now that things which we did earlier in the abrupt junction. Now look at the value. If Na is much larger than Nd, as the shown case here, xp0 will be ratio of Nd by Na times xno. Nd is much smaller than this, so xpo will be very very small compared to xno, or vice versa if it is n plus p junction. So please never make xp0 0, because then this inequality will not hold, and this equality will not, it will become an inequality. So always x0 exists, but this relation is always valid. Nd xno must be equal to nax. Is that okay? This is some kind of, if I multiply by q, what is this? It is called q on the n is equal, q is charge density, charge per unit area. Charge on the n side is always equal to charge on the p side, so it's called charge neutral across the junction. Qn is always equal to Cp. Per unit area, distance into per Cp is per unit area. So this is charge on the n, charge density on the left is same as charge density on the right. This we derived without even assuming this, we figured out by solving Poisson's equation. So E0 must be same, and E0 must be same, equality must be holding. Is that clear? On the left there are only acceptors, on the right there are only donors, but overall junction is still Qn minus Qp. Is this relation clear to you? This is very important in all derivations. You always use this very unknowingly or knowingly. It's okay, this I know, so other one I know. Is that point clear? Qn charge density, charge per unit area is on the n is same as charge per unit area on the right, always holds good for the junction which I have shown. So first say This is under thermal equilibrium. But the way it may happen, if something I apply and both go in the same sense, then this relation may even hold at any other bias as well if that happens. And I want to check that because you said you want the bias. I want to check does it happen. If it happens, I am very happy. If it doesn't, I will say what the relation is. It must happen in my opinion. But if it doesn't, then I will have to see this either again. We will see what happens if I apply bias. But till then, this relation is valid. Is that clear? So what is this method of calculation? This is phase charge analysis. This is diffusion layer is also called phase charge. Phase charge. Poisson's equation actually says V by dx is phase charge divided by permittivity. So actually this is the phase charge which we graph. All is clear? So let's come back. So what will happen in the linearly graded junction? Maybe we will solve that, but time permits. However, अभी जरा देखो थोड़ा सा क्या करते हैं. W is equal to XPO plus XNO is because net depletion width is equal to sum of XPO and XNO. But we just now wrote ND XNO is equal to NA XPO. So XPO is ND by NA X. So I substitute here. So now you can see if NDs are much smaller than NAs, W will be XNO, which is valid. That's what I was saying. If NDs are much smaller than NAs, this term is much smaller than 1, so this term can be. So I will use this expression till that value is known to me. So I keep this W is equal to XNO 1 plus ND by NA. Okay, what I was doing, let me check. Okay. Before I go ahead, some more relationship may be of interest. This is W. The voltage in the junction is V0. Voltage across the junction is V0. That we have said built-in voltage. So must be equal to dx dx. Is that dV0 by dx is minus E or E is equal to minus dV by dx. However, now I see from here, if this is an integral Ex dx, only place from where to where it is going? From XPO, because electric field only exists in this region. If you look at this curve or look at this triangle, what is the area? This is nothing but area. So what is the area of this curve? That is the voltage across this. Yes? Yes, W into E0, fine. Is that clear? Please remember, the base into height by half, triangle area. Area of the triangle is nothing but for the field is voltage. So integral Ex XPO to XNO is nothing but voltage, which is essentially W into E0 by 2. So now I can do little more calculations. I will derive V from Ex again. Use so many expressions I am writing. One I am going to use this, I am going to use this. From here you can see E0 is also 2V0 by W. This relation also I use. Same it, modify. Okay, so let's do some more maths on this. Please remember that I am using all these equations which I am writing. ये सब क्यों कर रहे हैं? The reason why I am doing all this, just a minute. All this great analysis I am doing, I want to find W as a function of VC. Is that correct? I want relationship between, as I keep saying, I went to this work because this young man came before all of you and told me, can you do this? I said, okay, dekhta hu, time milta hai to. So I am looking for anyway, I would have done it later, but so I want to know, is this depletion layer relationship with voltage? If I do that, then I may get what he is asking, because now I see very interesting. This is an ionized acceptors and donors like an electrolyte. This is neutral. So it has a small resistance, though it cannot be R0, but it is some resistance on this. So this is equivalently saying R series, C junction. There is another resistor here. Can you tell me where is another resistor here? We have not talked about current so far, but other day I did show you. No, it will be very large in the reverse bias. Very large. Small impedance, so we remove that. Large impedance. And the reverse bias. In forward bias, you will shunt the capacity. Or it will have some RC, whatever RC. So now I want to know what is this junction capacity. So he is insisting, so I said I keep it. इसको ऐसे बुरा कर. Okay. So as I said, my ultimate aim is to get, I neglect RS, and I say R is infinite, open circuit. So this is roughly equivalent to this. And now I see, if I see only this capacitance easily, if this is my W, let us say cross-sectional area is A, okay. So how much is the capacitance? What is inside that insulator, inside the depletion, which material? Silicon. So it is epsilon A into area by W. Is that clear? So, if I want the relationship of Cj versus V, then I must get relationship between W and V. So all this effort which I am now doing is to get this relation, because once I get this Cj versus V versus W, I can get Cj versus V. And if I get this, I have done something great. Why I am doing something great? Maybe I shall show you application first, then I derive that. None of you can say you have never used a circuit which is called tuner in some system or the other. टीवी ले लो, रेडियो रिसीवर ले लो, RF रिसीवर ले लो, मोबाइल, कहीं न कहीं आप ट्यून करते हैं, different bands, different frequencies. The tuner, which essentially is used for tuning any frequency, for example, there can be this kind of tune circuit or this kind of tune circuit, LC or RC, and in either case frequency will be 1 upon 2 pi RC or 1 upon 2 pi root LC. So if I want to change the frequency of this so-called resonant circuit or tune circuit, R is normally fixed, L is normally fixed, so I must vary C. So one method of varying C is to change the W itself. So earlier, I don't know any one of you has seen capacitance which used to be called condenser. Have you heard of a word condenser? There are plates which are put inside each other, and when they open, many plates come closer, otherwise the gap increases. There is a rod there, two plates, this plate, two plates. So this net capacitance can be varied because the air gap will change. Now those are called condensers. So we said okay, अभी तो mechanical हो गया. पहले सब रेडियो सेट रिसीवर्स में वो जो आप घुमाते थे ट्यूनिंग, वो एक्चुअली अंदर कंडेंसर का रॉड घूमता था. Now we said this is too clumsy, too much big area it takes. So why not we do something voltage dependent? So we started calling new oscillators which uses this are called VCO. What does that mean? Voltage controlled oscillator. So I want to change voltage, and because of that I will change the frequency. Is that correct? If I have to change frequency, I see C should change with C. If I change V, I must change C. If I change C, I change the V. Is that correct? This name of this capacitance which varies with voltage is called varactor. Or in market, varicap, variable capacitance. Market it's called varicap, we call it. Why react? They are variable reactance, so varactor. So we were really looking for relationship between J and V, because if that happens by changing V, I change C. If I change C, I can change the frequency of operation. Is that clear? So this is the use of this. This is the use of capacitance. There are many uses, but since in your lab there is no experiment on this, so I thought I will tell you this is the major application which we actually use in almost every analog digital circuit where you generate something. So when you generate signal, this is how you measure it. Okay. So is that point clear why we are doing? Okay. Let's do some quick another evaluations. Okay, now attention now. We again derive V0 from electric profiles. Actual electric field only exists between XPO and XNO, minus XPO to XNO. थोड़ा मैथ सिंप्लीफाई करने को बोला, लेफ्ट साइड राइट साइड डिवाइड कर. Okay, so if I substitute these values, what was the expression here? Call it minus V0 is minus XPO to the power into 0 QNE. क्या expression है? V0 upon Ks epsilon 0 into dx plus 0 to xno 2nd x minus xno by Ks epsilon 0. Please check. मैंने लिखा नहीं, इसे देखो. आपको डिराइव किया ना, अभी वो एक्सप्रेशन देखो. ये माइनस साइन तो मैंने उधर कर दिया, इसका माइनस प्लस कर दिया. So if I differentiate, integrate, what will happen to this term? X square term will appear, x square by 2. This will become xp0 into x, constant है तो भी, और ऐसा ही इसका भी होगा. So if I do this analysis, please do yourself. I have just give the final answer for you. QNA xp0 square upon 2ks epsilon naught plus कर दिया सब साइन now, plus QND xno0 square by 2ks. In many of this, the third relation I have used, nd xno is any, I can use even this expression wherever I need. Okay, so I am giving you so many expressions. ये भी एक expression है. Okay, fine. How much? अच्छा, another term I need. Okay, E0 यहाँ लिखा है. This is also equal to QND XNO by Ks epsilon naught is equal to QNE with sign taken care, XP0 value only. This also I may not need. All these expressions I have derived for you. Okay. You have noted down this? Maybe I will rub that side. I am using this expression. W is equal to 2V0 by E0. थोड़ा रुको भी भाई, मेरी घड़ी में कितना है मैं देख के बताऊँ. अभी तो 15 मिनट है यार. Just a small, please. This may take few minutes. Please. तुमने कभी 1.5 घंटे का क्लास अटेंड नहीं किया लगता. अभी तो मैं आपके नया इसलिए ज्यादा नहीं बोला, नहीं तो 3-3 घंटे भी पढ़ा सकता हूँ. अभी आप टेंशन मत लो. Please, we'll finish this few minutes. Please. Okay. Whatever I was deriving, I will not derive. Next time I will start it. Whichever way you. If you feel so that, if you don't want to learn also, it's fine enough. We'll only have midterm intent. Your choice. If you feel this is all irrelevant, then just not have it. Please do not treat me so easily. Don't think that I can just pardon you on that. And I accept, I like people, young people are my most favorite ones. But let's not behave otherwise. So if I do this, I get Q in NAXP0 is this, so I can derive one of them. ND square XNO square upon E0, sorry, Ks epsilon 0, 1 upon NA plus 1 upon ND, Ks epsilon 0 divided by Q ND. XNO. E0 is substituted here. This is taken out, 1 upon Na plus 1 upon Nd. This QNA XNO or this can further cancel because of this relationship. And finally, what you are going to get is width is equal to 2Ks epsilon 0 V0 by Q, then W any nd by any plus nd to the power minus 1, or final word, collect the terms of w. So w square is twice ks epsilon naught y cube any plus nd upon any nd, or w v0 what I did is I wrote w is equal to 2v0 by e0. v0 I took that expression which I derived, that was only Na, so I made Na square by Na and Nd square by Nd. I write 1 upon E0 by this term, collected the term, this I took out. This term will then become from W relationship in this form, replace xno by this from xno from here, so I'll get in terms of W that value. So I get this expression, W is equal to twice k epsilon naught V0 by Q into W Na Nd, Na plus to the power minus 1 upon that. If I collect W, I get W square is twice k epsilon 0 by Q, Na plus Nd upon Na Nd into V0. Is that okay? So the depletion width goes what? Proportional to what? Root of V0. Is that correct? Root of V0. And inverse root of doping. Now quickly before we leave, if NAs are much larger than ND, which term vanishes? 1 by NA. So for this case, W is equal to twice Ks epsilon naught QND. Why it is so? What is it trying to say? That all the depletion layer in a P plus junction will go towards N side. So that is also proved that almost all the depletion layer will be on the N side, because 1 upon Na will be much smaller compared to 1 upon Nd. So Nd may decide the depletion layer, not as much as Na. In opposite case, it will become Na, then it will be P side which will deplete compared to N side. Yes, Prof. Right का क्या? No, Na is on the P side, Nd is on the N side. If NAs are much larger, this term will be smaller compared to this. So you neglect 1 upon Na in terms of 1 upon Nd. Okay, so you will get this expression. So the depletion layer is only on the N side if P plus N junction. XP0 is not 0. All derivations we say XP0 is not 0. We are just derived this. If NDs are smaller than Na, almost XNO is 0. Is that clear? So this expression also says same thing. All the depletion will occur in N regions of P plus N. Almost all. But there has to be XP0, otherwise this relationship will not hold. Is that clear? If I know W, then what can I get? W, of course, we will apply voltage next time. If I know W as a function of V, then I know capacitance as function of V, because C is related to W, I just showed you. So I know C versus V, so I can always get relationship of C and V. That's correct. So we'll come back tomorrow.